right, we are back. This is Calculus 1. We are looking at Chapter 6. Well, not all of Chapter 6, like half of Chapter 6 on differential equations. So 6.1 differential equations in your note packet. And I got haircut. Actually, I got them all cut. We're on page 2. So let's take a look at page 2. And we'll jump in. So a differential equation, you can write this on the way top of the page. A differential equation which we will refer to as a DE has derivatives in it. So we're going to be building on, we've played around with these a little bit already in chapter 5. And so examples are like dy dx is equal to 2x plus 1. That would be, this is a differential equation because I can have dx over there, multiply both sides by dx, and you got dy equals. Another example would be if you have something like y is equal to 3xy prime plus 2y double prime, something like that. All right. So on the example underneath, differential equation in x and y is an equation that involves x, y, and the derivatives of y. All right, a function y equals f of x is called the solution of a differential equation. A solution, not the solution, a solution. If the equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. So let's take a look. It says, for the example, show that y equals e to the negative 2x. That is the solution, a solution to the differential equation. All right, that's an equation. And then this is y prime plus 2y equals 0. This is the differential equation. So that's the differential equation. This is a possible solution to the differential equation. And we're going to find out right now. So you say, okay, well, y is equal to e to the negative 2x. So y prime plus 2y, does that equal 0? Because here, let's do y prime. Y prime, when you take the derivative of this, so they said y is equal to, y prime is equal to, so remember how to do the derivative. The derivative is itself and then times the derivative of the power. Remember how e to the x works. So we got e to the negative 2x, but then times the derivative of that, which is negative 2. So y prime is negative 2e to the negative 2x. So now what we do is we take this, put it there, we take that and put it there and see if we get 0. It doesn't always have to equal 0. It could equal 10 or it could equal something else. It's not always 0, but in this example it is. So we pop in negative 2e to the negative 2x plus 2 times e to the negative 2x. Does that equal 0? And I've already seen shorthand like this as like a little question mark above it. But really, if it doesn't equal 0, at the end you just do a not equals to sign. So negative 2e to the negative 2x plus 2e to the negative 2x. Well, those are opposites, so that is 0. So 0 equals 0. So the answer is yes, it is a solution. Then y equals e to the negative 2x is a solution. right? So let's see. It can be shown that y equals c times e to the negative 2x is a general solution of y prime plus 2y equals 0, where c is any real number. Choose any value of c and show that it works. Okay. So we'll keep it simple. We won't pick 1,282 or something like that. How about we pick 4? 4 is pretty easy. So we're going to say that let c equal, negative 4. All right, negative 4. That's a number. Any value of c and show that it's equal to. So c is equal to negative 4. So then we want to say the solution would be y equals negative 4 e to the negative 2x. Y prime would be 8 e to the negative 2x. And then y prime plus 2y equals 0. So we're going to take that plus that times 2 and show that 8e to the negative 2x minus 8e to the negative 2x is in fact 0. So that would work with any number. 0 equals 0. It's not always 0, it just happens to be for this example. All right. So there we are. So let's check examples. Determine if the following functions are solutions to this differential equation. Y double prime minus y equals 0. All right, well, let's see. Again, it's not always equal to 0. That's just happened to be in the first couple examples. So our differential equation is y double prime minus y equals 0. They want to know, does y equals sine x work? So we need both the second derivative. So we can't find the second derivative without doing the first derivative. So you got to go to your way back machine, right? Sine, cosine, negative cosine. Remember that? And so y prime is equal to the cosine of x. Y double prime is equal to the negative sine of x. And now we're going to look at negative sine x minus sine x. Does that equal 0? I do not believe it does, because those are both negative. So it's negative 2 sine x, which does not equal 0. So that is our conclusion. It is not a solution. Then y equals sine x is not a solution to the differential equation. All right, let's see if we have better luck with the second one. Y equals 4e to the negative, what does that have? Man, that's a tiny letter, negative x. All right, so y prime is equal to negative 4 e to the negative x, because remember the 4 is out front, you do the derivative, and then the derivative of that's negative 1, so that's where the negative came from. And then double prime is, again, same situation, but it's just going to flip back to positive 4e. All right, so now let's take a look. Double prime minus y, does it equal 0? Is 4e to the negative x minus negative, oh, nope, just minus, not, I almost did minus the prime, just minus the original. minus 4e to the negative x. That is 0. So then we conclude then, we get to say y equals 4e to the negative x is a solution. And then for the third one, they want us to show for any constant c that this is always going to work. If you put in any number here and then e to the x, that any number would work. So y prime would just be c e to the x times 1, right? So that's just that. Y double prime is c e to the x again. And so y double prime minus y, does that equal 0? Does c e to the x minus c e to the x equals 0? It does. So any constant, then y equals any constant c e to the x is a solution to the differential equation. All right. Okay, let's look at page 3. I don't know, how am I going to do that? Geometrically, the general solution of a first-order differential equation represents a family of curves known as solution curves. The general solution, x, y prime plus y equals 0, is y equals c over x. So the solution, so you could put any number over x. Note the solution curves for c when it's equal to -4, -1, 1, and 4. So here, I'm just going to show you this. I'm not going to try to draw those on the board because I'm not going to do a good enough job. So just pointing these out, that's y equals -4 over x. That's y equals -1 over x. This is y equals 4 over x. That's y equals 1 over x. Y equals -1 over x. Y equals -4 over x. Y equals 4 over x. Y equals 1 over x. All right, so you get the general idea. We could take a point. One ordered pair could identify which one of these, any of those. So if I gave you an ordered pair, 2 comma whatever it is, then we'd be able to identify this. And we're going to do that coming up. So that is solution, all the solution curves. And those are only 4 of them. There's an infinite number of them. You could put in any value you wanted. -5, -20, +30. Any of them would be the same, just in a different part of the graph. All right? Okay, so let's look at the order of differential equations. So the order is the biggest number of derivatives. So the first derivative, second derivative, third derivative. And remember, we could find fourth and fifth and sixth and seventh derivatives. So that's the order. So if you had a second derivative in your differential equation, that would be of order 2. This is an order 2. So the order of differential equation is determined by the highest order derivative in the differential equation. So here's an example. You can squeak down in there. 2y double prime, and we'll make this really ugly, plus 3 to the 7th y triple prime minus 2xy equals 9y prime. So there's our differential equation. This is order 3. Because then the solution has 3 arbitrary constants. All right? Or sometimes it just say third order. So. that, then the solution has 3 arbitrary constants. Okay, so let's take a look. Example using position and acceleration. Given the differential equation, S double prime of t equals negative 32, and the general solution, S of t, equals negative 16t squared plus c1t plus c2, show that S of t is a general solution. Okay, so remember how this works. Right? S the position, V the velocity, A the acceleration. And so we knew, what do we know here? S of t is equal to negative 16t squared plus c1 of times t plus c2. So S prime of t is equal to negative 32t plus c1, c double prime of t is equal to negative 32, which, I mean, they gave us that, and, I mean, we just figured it out. So check in DE. So negative 32 does equal negative 32, right? They gave us the differential equation that the double prime is equal to negative 32. So that was our check. Basically, this kind of checked itself. We got right here and knew it was negative 32, and that's what they gave us. But here's the official check. We took that number, replaced it with that, and that equals that. So then S of t is a solution. Now, for this same problem, for part B, they say use the initial condition S of 0 equals 80, S prime of 0 equals 64, and find the particular solution. So we have a general solution right here, but it is a second order differential equation, right? And 2 arbitrary, there they are, C1 and C2. So basically we have to find C1 and C2. This is a general solution, and we want a particular solution. And so we're going to find that by just taking S of 0 equals 80, which means, this is part B. We put in 80 is equal to negative 16, 0 squared plus C1 times 0 plus C2, which produces C2 is equal to 80. Then we take S prime of 0 equals 64. And now we're going to take that and say, okay, well, 64 is equal to negative 32 times 0 plus C1 and so then that goes to 0. So now we know C1 is equal to 64. So now we have C1 and we have C2. And so now we have a particular solution. I've seen it in other texts also as a specific solution, but particular, this one goes with particular, which is fine. All right, so S of t is equal to negative 16 t squared plus 64t plus 80. And so basically we have conditions, initial conditions on S and S prime that allow us to calculate these arbitrary numbers. So we get a particular solution instead of just a general solution. Okie dokie. let's look at page 4. So, doing for time. Good. All right, so verify the general solution satisfies the differential equation, then find the particular solution. Okay. All right, so number 5, we got y is equal to c x to the third x y prime minus 3y equals 0. That is our differential equation, and y equals 2 when x equals 3. So we need that to find our particular solution. So we'll confirm that this is a possible solution. So for number 5, so y prime, we need the prime. Y prime is equal to 3. C is a constant, so let's just say c, x squared. And now we're just going to take that and put it in there. We're going to take that and put it in there. We're going to leave x alone and then confirm that that's 0. So we have x times this, 3cx squared, minus 3 times this, cx cubed. Does that equal 0? So we need that to equal 0. So x times, remember there's no distributive property here, it's just x times 3 times c times x squared. So that's 3cx cubed minus 3cx cubed, which is 0. So 0 equals 0, that's confirmed. Check. So yes, it is a solution. All right, now find the particular solution. So we're going to take y equals cx cubed, and we're going to put in 2 is equal to c times 3 cubed. And so 2 is equal to 27c divided by 27. So 2 27ths is equal to c. So now we can go back to this original y and find the exact, or not the exact, the particular solution. 2 27ths x to the third. That is our particular solution. This was a general solution they gave us, and we confirmed it. And then this is the particular solution that matches with these initial conditions when x is 3, y is 2. Okie dokie artichoke. All right, let's look at number 6. Use integration to find a general solution of the differential equations. Okay, so we've done this already. This is kind of from chapter 5, so this is going to be a little bit of a repeat there, which is fine, right? That's fine. So remember when we had dy dx, and then we want to write it just as dy, so kind of separation of variables here. We multiply both sides by dx, basically. those cancel, and now you got x, 1 plus x squared dx. And so now we're going to integrate. We'll call this 1 over 1 plus x squared x dx. We'll use u substitution, 1 plus x squared, so du is equal to 2x dx. And then I look and say, oh, I got x dx, and I don't got that 2 there. So I got to divide out 2, so 1/2 du is going to be substituted for x dx. And so this is going to become that. That's going to become u. This I could integrate already, right? That's just y. And then this is 1/2, because the 1/2 will squeeze that out front. And 1 over u du. And then remember how that works. So that's u. 1 over u, we have to use the natural log. ln plus c. Remember the plus constant, always with the plus constant. And now put that back in. And so there's our y equals 1/2 ln the absolute value of 1 plus x squared plus c. And there we have it. That is our general solution. And we did that, right? We did that a bunch with the dy dx stuff from chapter 5. So hopefully that's just tying it in for you a little bit. Let's look at number 7. So we were doing differential equations. We weren't doing diffie already. And a little bit of the separation of variables, which we will look at in greater depth. And later in 6 here. So then number 7 is y prime is equal to x e to the x squared. Man, that is tiny to my old eyes. X squared. All right, so let's rewrite it. And it's y prime, that's Newton. We kind of want Leibniz for this. It's better. Let's call it dy dx. And then do the same thing we just did. Multiply both sides by dx. So we've got dy is equal to x e x squared dx. And now integrate. So y is equal to, let's say u is equal to x squared. Let's say du is equal to 2x dx. And we got an x dx, but we don't have a 2. So we got to divide out that 2. So 1/2 du is going to be the substitute for x dx. So we got x dx, but we're going to put in e to the u, and then we're going to squeak that 1/2 out front, and then the x dx is just du, because we already put the 1/2 over there. All right, and so then you do the actual integration. So that is 1/2 e to the u plus c. And then don't stop there, don't stop there. Remember, you got to put that x squared back in there. So y is equal to 1/2 e to the x squared power plus c. Just like that, just like so. And that is all there is for 6.1.